Rotation about a fixed axis. Consider a rigid body, shown in blue, that rotates around a fixed axis. We'll align angular velocity of rotation along the coordinate component z axis. The solid body, broken into little chunks m alpha, will have some total angular momentum. Now, ahead of time, we cannot assume that this angular momentum will be aligned with omega. So therefore, we'll show it to be generally pointing elsewhere. We write total angular momentum as a vector sum of angular momenta of all the chunks alpha, which of course is nothing other than position r alpha cross mass alpha times r alpha dot. Note that the velocity r alpha dot is entirely due to rotation around this fixed axis, which we write as omega cross position r alpha. We know that we can write the z component of the total angular momentum as being proportional to the angular frequency omega of rotation, where the coefficient of proportionality is simply given by the sum across all of the chunks alpha of transverse coordinates relative to the axis of rotation, x alpha squared plus y alpha squared. This, of course, is nothing other than the moment of inertia. In particular, we note that kinetic energy can be written as half of moment of inertia, I sub z, times omega squared. In other words, moment of inertia acts as mass. But there is a caveat. This is because we also have x component of the angular momentum, which will simply be given by the mass of m alpha times x alpha times z alpha times omega, from the definition of above, where of course x and y coordinate system is perpendicular to z, which we can write as I sub x. Similarly, just from the definition of the cross product, we'll find that L sub y, the total momentum, will be given by minus sum m alpha y alpha z alpha times omega, or I sub y omega. And of course, there is no particular reason in general for either I sub x or I sub y to be equal to 0. The result that we get is that total angular momentum generally will be wobbling around the axis of rotation. In other words, its time derivative, L dot, will not be 0, because L is not constant. Well, whenever we have a derivative of momentum or angular momentum, that implies the existence of some force. In other words, we expect that L dot is defined by force, general force, which in this case is torque. And we find that generally one needs torque to maintain rotation. And that's why we balance tires, for example. We will summarize our result In a more general notation, we will write that the three components of the total angular momentum will be given by coefficient I sub x, and then we give a second subscript z, which will indicate that in our choice of coordinate system, omega is parallel to z hat. Likewise, for the y component will be I y sub z omega, and then I sub z z omega, which will describe total angular momentum vector.